the city. That's fine. I'm Bruno, so I'm very happy to welcome you all here. That's the first time we organize, at least, in Hadron Physics an event on this campus. This conference was supposed to take place in 2020. I think I spoke with Abe in 2019 in Paris, and you know for which reasons we had to postpone it several times. It finally takes place. I would have expected maybe a little bit more people, but we're about 50. We're going to have 27 talks, more or less. I'm quite happy we have some good national representation. I think some eight talks by Brazilians. There's going to be posters too. It's going to be some thin posters. We also have a fair contingent of people from Mexico and Colombia, so this Latin America is represented. I couldn't get anybody from Argentina and Chile, but well, with time maybe. And so this whole conference, the idea is really, you have AIC meetings in the US, is to make it actually more palpable or address more people here in Brazil and in South America and Latin America in general. And so attract young people to maybe to this physics. And so that's the reason I told most people, look, give more overview talks, make people want to do it. And we will have also on Thursday night, we'll have, you probably saw, we'll just have an open mic roundtable about possibilities, opportunities for the EIC in Latin America. All right? So we have talks, we have a 2-hour break. I sent you an email yesterday. During that break, there are several restaurants here in the surroundings. We're close to the Paulista Avenue. And if you have any questions, you can ask the staff, but you can ask directly me. And we should actually, I want to have Nora talk a little bit about the institution here because it's pretty recent and what its purposes and aims are. Okay.
Thank you very much. I'm Norma Regiani and I work here at the Principia Institute. And I'd like to welcome all of you. It's really a pleasure to have another conference workshop of the ICTP Safer here at the Institute. The Institute has 3 kinds of work. We devoted to scientific research as this conference here. The one work devoted to outreach research and scientific outreach, scientific devoted to young people, and a school that has young people, still students of the medium school, that has very good abilities to physics and mathematics. All these 3 activities happens in this building here that soon will be a digital dome, and in the very beautiful old house here in the entrance of the place that is, of course you have seen, and the building that is just nearby, that's a new building in the center in which we will have the coffee break. So welcome, nice to have you here.
All right, I should also say, I've organized events before all on my own, so having this infrastructure of the ICTP, having people like Humberto and many other technicians. Jean Dever is not here, the secretary you probably had to deal with too, around really to acknowledge his help would make my life much easier. And also the support, so the ICTP offer generous support. You know, I think everybody's hotel is covered. And also JLab and Brookhaven that were really helpful. And that makes life very easy. So thank you also to the people who help and sponsor this event. And with this, I pass to Abe, who's going to chair the first session.
Well, thank you very much. It's a delight to be here. Finally, as was mentioned, that we had planned this event 2-3 years ago. And I'm very delighted that finally we are coming here with this audience. And over those 3 years, and since the first meeting that happened in South Africa, about 10 years ago, 12 years ago, EIC has moved on very significantly. So today you're going to hear from the first time what the science and the status is from Elke Aschenauer, and then we'll go into some other talks which are related to the EIC. So Elke, please open your mic up.
Yes,
You have a mic,
I.
okay.
Can you hear me? Or should I put it a bit higher? Yes, maybe that. Huh?
So you have 15 minutes. So give you a warning at 10.
Yes.
10 minutes. Yeah.
Okay. Good. So let me say it is an extreme pleasure for me to come to Brazil. It's my first time, and it's part of my favorite part of the world, South America. So I'm really delighted to be here. And to tell you where we are actually with the Electron-Ion Collider and why I think, and I'm completely convinced about, it's a worldwide, absolutely unique collider to unravel the mysteries of visible matter. And I will tell you about the science, the experimental part, and where we are with the project, and where is the chance for you to actually kind of work with us. Should this work? I do the laser work, but it doesn't move forward. Should I try again? Okay, so thank you. So for the people which don't know what the EIC is, so it is a high luminosity, and that means 10 to the 33, 10 to the 34 polarized electron-proton-ion collider with a wide range of center of mass energies. And I will tell you why we need actually that. What is special about it? The EIC is, if you look worldwide, the only new collider which is really getting built. There's a lot of plans for 2060 and something like this, but we are really doing it, and it is actually allowing us to remain at the frontier of accelerator science and technology, and I will show you that as well. We have, compared to HERA, a factor 100 to 1,000 higher luminosity, and both the electrons and the protons and light ions are polarized. We have nuclear beams up to the highest masses, so uranium. And if we look to fixed target facilities, we of course cover a much wider range in X and Q square, and I show you this. We will have really, for the experimentalist, a state-of-the-art general purpose collider detector, and we will answer some really unique science questions which are there for many, many years. So, why do we need actually a new collider? And it is very easy because we want to show complementarity. And QCD has actually two concepts which lay its foundation, which are factorization and universality. And if we really want to see whether what we see, if we do a measurement, whether that is interaction dependent or whether it is a phenomenon which is an intrinsic nuclear property, we need different complementary probes. And these probes are high precision data from EP, PP, and E plus E minus colliders. And only if we have all of them, then we can actually really fully unravel the picture of the nucleon. So factorization, what that basically means is that if we have a cross-section, we have our parton distribution functions, then we have the hard scattering, which we can calculate from first principles, and we will hear a lot of talks about this. And then we have the hadronization. And what actually factorization means that we can write it down like this. The PDFs and the hadronization, we can at this moment not calculate from first principles, so we need to measure them experimentally. But if we put it together, we calculate this cross-section, and then we get the right thing. Universality means that if we measure these parton distribution functions and extract it, for example, from the HERA data, which was at a 0.3 TeV, and then calculate the cross-section exactly like this in PP and proton-antiproton from 200 to 7 TeV, then we can actually describe the cross-section. And for the unpolarized collinear PDFs, that actually works really beautiful, as you can see here. Okay, so we have the different processes. We have hadron, where the probe already has a very complex structure. We have no simple access to parton kinematics. We have some rough access to PDT and PT, gives us an X and Q square, but they are very strongly correlated. And the gluons, one advantage in hadrons is that gluons, of course, come in at leading order, so you can actually study very nice, for example, gluon fragmentation. Then you have electron-hadron scattering. You have a point-like probe, which has a very high resolution. It gives you actually partonic kinematics through the scattered lepton for every single event you have, so you get X and Q square. You can separate initial and final state effects cleanly via looking to inclusive measurements and then also measurements which are semi-inclusive. And then in between, basically the bridge between both of them are ultra-peripheral collisions, which we do a lot at RIC and at the LHC. You have a photon-induced probe, but you have, again, no simple access to partonic kinematics via rapidity and the mass. You can get x and q square, and you have mainly access to the initial state and not to the hadronization. So here again, DIS, we have the electron emits the virtual photon, we scatter. The whole process is governed by this very simple equation where you have q square, which gives you the resolution, S, which is the center of mass energy, X, which is the momentum fraction of the partons inside the proton, and Y, which gives you the inelasticity of the process. And here we have a very nice graph where you can actually see that you have scatter, you get the virtual photon. Why do we need large kinematic coverage? So why do we want a machine which has actually a wide center of mass energy of 20 to 140 GeV? Because we want to access x and q square over the widest range, because if you look to the proton and you change it from high x to low x, it actually really changes how you actually see it. At high x, it's basically dominated by the valence quarks, and if you go to very low x, it's a pure gluon state. And you really want to see how this transition actually happens from high to low x. So for the EIC physics, and I will give you examples for all of this. I give you first a high level, and then I go in more detail. So what we want to do, we want to see how C quarks and gluons and the valence quarks actually get their spin. So how is the proton getting its spin? How are these quarks and gluons distributed in space and momentum inside the nucleon? So we want to go away from the collinear picture and really kind of have a 3D picture. And then we want to see how do nucleon properties, like the mass and so on, emerge from the interactions of these quarks and gluons. And then we put the protons and neutrons inside the nucleus, and then we look actually similar things. How do actually then change what we have been seeing on the proton? How do the PDFs and so on change? How do the interactions create nuclear binding? And how do actually, if we have hadrons coming from the quarks, how do they actually change the hadronization if it happens in a nucleus or it happens in the vacuum? And then last but not least, we want to create, by having actually nuclei, the highest nuclear densities, and want to see whether we can reach a state which we normally refer to as saturation or nonlinear QCD effects, where actually the gluons, which can split in gluons, gets balanced by that we have so many gluons that they don't have enough space anymore inside the proton, so that they get recombined. And I will show you for all of that examples how the EIC can actually measure this. So the path to imaging quarks and gluons. So we have our very well-known collinear parton distribution functions, which tell us what is the density of quarks and gluons and C quarks inside the proton. And we had this really nice measurements from Hera, which basically show that at low X, the proton is completely dominated by gluons. Okay, so then we get a bit more complicated, and we look how is actually the quarks and gluons transverse momentum distribution inside the proton, and the same for the spatial distribution. And then actually recently we have figured out how we can measure Wigner functions, which in some other, like solid state physics, is kind of very common. So there we can get the longitudinal, the transverse momentum, and the spatial distribution of quarks and gluons inside the proton at once. And then, of course, all of this is also correlated to form factors and the generalized parton distributions, which we are. So a reason why we are doing this is because we really want to get a much better picture on nucleons and nuclei, and we want to understand collective effects. And if you don't have a 3D picture, you could think, okay, she's eating her baby, but actually she's only carrying it. So 3D pictures give you much more information, and something which is really important if we want to understand the proton. So now a couple of examples. Here you see actually the semi-inclusive cross-section for kaons measured over a wide range in X, and also C, which is the fraction of the hadron carried compared to the virtual photon. And then the different colors are Q square. So you see an enormous precision, wide range, which we can cover. And as an example, here is an extraction on how well we can actually strange PDF, something which is basically not known right now. Here you see actually the light gray is our knowledge right now. And the dark one is after we put this cross sections, which I just showed you, into kind of PDF fits, because it is kaons which are most sensitive to strangeness because they have a strange in the valence quark. Of course, we need also to know the fragmentation functions. And what this paper here has shown is that you basically need a fit, and what a lot of the groups are now doing, where you fit the PDF, the fragmentation function at the same moment. Okay, so that is collinear PDF, the strangeness. We can do exactly the same for the nucleus. We measure the inclusive reduced cross-section over a wide range in X and Q square. So you get basically the scaling violation plots you need, you know, from HERA. Green is actually the data which we have right now. So you see that the EIC expands this enormously. And then if we look how well we can, for example, measure the gluon distribution inside a lead nucleus compared to the proton, then you have here in light gray the best knowledge which we have right now, based also on the LHC PA data. And then you see here in the blue kind of, if we include the inclusive cross-section and the charm reduced cross-section, and you see we can really constrain versus the gluon distribution in a nucleus is different or the same as a proton, which right now we maybe have hints that it is different, but not really a precise measurement. So then the spin of the proton. It's a very, very interesting quantity, because the spin of the proton is, of course, one of the absolute quantum numbers which you have for particles. All of them have it apart from the Higgs. The Higgs is the only particle which doesn't have spin. So you have a contribution from the quark, from the gluon, and from the angular momentum. And actually the key observable is to measure structure function, which is G1, with the proton and polarized helium-3, and then you get the quark contribution and the gluon. And then you can also do double spinor symmetries where you tag actually a hadron in the final state, like a pion and kaon, and then you can actually get a flavor-separated polarized quark distributions. And what you see here is actually the structure function G1 measured over a big range in Q square and X, and the current data sit in this very small corner, because apart from RIC, all other data are coming from fixed target. And as I told you, of course, the XQ square range then is very limited. So if you take this and you look then, what is the contribution? How well can we actually measure the quark and the gluon contribution and the orbital angular momentum? Then you see here the dark blue is if you have the full kind of energy range, you kind of constrain them. And then depending on what comes out of the measurement, if you would have an orbital angular momentum of 0.5, 0, or minus 0.5, the ellipse would kind of move around here along these lines. So with the EIC, you can see you can measure very well the different contributions to the spin of the proton. Something extremely important is actually to understand how the proton looks in spatial distribution in 3D. And there's a lot of connection to other fields, and one of them is here. At the LHC, in lead-lead, in p-lead, and in proton-proton, with high multiplicity events, we have seen this collective phenomena, so which are kind of called the rich. And they are very interesting. So in lead-lead, it's something which you expect, but in the light kind of combinations, you don't. And there have been very nice papers by Heikki and Björn, which describe actually this. But the biggest uncertainty to actually describe why you have a rich in PA and PP is because you don't know how the proton looks in 3D. So you don't know, does the proton look like this, how are the fluctuations and so on. And actually the EIC is exactly the machine which can measure this, and particularly for the gluons also, how they are distributed, and the quarks, because we can do spatial imaging in 3D. And I show you in a minute how we do this. So what we do, we use actually a process which is exclusive. That means we have a virtual photon. It scatters on a quark or a gluon inside the proton. The proton stays intact and gets a momentum transfer to it. And then you produce either a real photon or a shape psi if you want to study the gluon. You see here actually the XQ² range, which the EIC can cover from here till down there. And you see these points which are spread around, which is actually showing what is measured right now in fixed target. And then the dark points here is HERA for deeply virtual Compton scattering, which means that you have produced a photon in the final state. So here you see how well we can measure the cross-section as function of t. And then, of course, if you want to have the spatial distribution, pt square is the Fourier conjugate to the spatial parameter bt. And that's exactly what you do. You do a Fourier transform. And that is how well you can actually measure the spatial distribution for a particular x and q² bin here. And then the same you can do for the shape psi. And you see how well you can know the spatial distribution for the gluons inside the proton. Now we can do this over a wide range in x and q², and that is what you see here. So here is a fixed q², and you change x, and you see that from high x to low x, actually the proton, that is for the proton, it grows. And here you do that for, yes, it's the same for shape psi. You have here a fixed q², and again, the models predict that your gluon actually at high x sits more in the center, and then at low x here, it covers a much larger range actually of the spatial distribution of the proton. What is very interesting is we can take exactly the same measurement and do this on nuclei. So we again scatter a virtual photon on gold. We produce a shape psi, a phi, or a rho. And then we get the coherent scattering amplitude, which means that the gold nucleus doesn't break up, so you coherently scatter on the nucleus, or you get the incoherent, which means that you scatter on a proton inside the nucleus, but the proton stays intact. So if you take the Fourier transform of the coherent one, you get the spatial distribution of the nucleus, which is very interesting, and it's something which we really want to understand. And if you take the incoherent, what is very nice is actually it gives you how much the fluctuations of your nucleus are. So in which configuration it is and how these configurations are changing. And that is something which is extremely important for many heavy ion collisions, which we are doing, because we want to really understand what is the source we are scattering from and how these fluctuations, for example, impact also some of these V2s and so on, which are measured in heavy ion collisions. So, last topic, but very important is, as I said already, we want to actually study nonlinear QCD effects. We have seen from HERA that very soon the proton is completely dominated by gluons if you go to low X. So now if you take actually a nucleus, you have a virtual photon, and the nucleus has all of this at high energy. It basically forms a wall of gluons, and then you scatter coherently on this wall of gluons. So what happens is that actually enhances that you see that you have recombination of gluons, and you get this nonlinear QCD effects, and the enhancement goes actually with the mass of the nucleus to the power 1/3 over X. So if you want to do the same measurement in proton EP, then you need actually a factor of 200 lower X than you get with the nucleus. So it's actually a very nice and cost-effective way to lose nuclei to actually study nonlinear QCD effects. So what is one of the golden probes? I will not go through all of them, and I show you one as an example. What you can do is you look in proton nuclei or in EP, you look to basically dijets or dihadrons, and you measure actually how many backward jets you have compared to the first one. And if you have nonlinear QCD effects, you get actually a disappearance of the second jet, or you get a decorrelation. And this is exactly what STAR measured. And I apologize for this. It's probably Mac to Microsoft. What we measured here is, you see here's the decorrelation, the second peak, how many we have. That is for PP, P aluminum, and P gold. And at the lowest X, we see a nice suppression basically of a factor of 2. And if we go into a regime in X and Q square where you shouldn't expect any kind of saturation anymore, then exactly it disappears. So we have measured here, if you put your head to the side, you see how much the relative area of this peak is suppressed, and it follows exactly the models which have saturation built in. So it's actually too nice to believe how perfectly it fits with this A to the 1/3. What is very nice is we can also measure the X dependence here, and we have measured the mass dependence between P gold and P aluminum, and you see exactly it follows what you would expect. So the EIC can do exactly the same thing. And what is very nice, because we can control the kinematics so well at the EIC with the electron, we can really step down in X at a fixed Q square. And that is what you see here for different center of mass energies. If you move down here, how much you get suppression, basically a factor of 2. And that is the same kinematics as we have in STAR, because it's the same X and Q square coverage. And then a quick slide on jets. Jets have become a big probe now also at the EIC. You can do and say it's the best method, of course, to kind of come back to the pattern kinematics. We can really study that well. We can probe showers. We can look to hadronization. You see here's a different kind of properties which we can understand, and examples how well the EIC can do that with papers which have been published on this. So now you have a physics case, all very cool, but you need, of course, also an accelerator which can give you the data. And that is what we have. So we use RIC, the hadron beams, and make major modifications to this. We built a new electron machine with a very new electron injector for polarized electrons. We changed the hadron beam significantly. So the hadron beam will be 40, 100 to 275. We use the injector complex from RIC. We have a high beam current. We have the light ions polarized up to 70%, and we have the nuclear beams. And we are working on also to realize a new concept to go to the highest luminosity of strong cooling, which we want to cool the beam so that we have the smallest densities of the highest densities in the smallest area of the beams. For the electrons, we have 5 to 18 GeV. We limit our beam current because of the synchrotron radiation, but we have 2.5 amps in the machine. What is very impressive is we have 10 nanoseconds bunch spacing, which is much faster than the LHC, which has 25. And we have 1160 bunches, and also the electrons are polarized very highly. We have the electron rapid cyclotron, which is the injector to the electron beam, which has 100% spin transparency, and it's a new concept, hasn't been realized at all in accelerator science to inject polarized electrons. And then I will show you we have a very high luminosity interaction area, which utilizes a crossing angle and crab cavities, and I show you what we do there. So here you see the machine, and you see all the new things which we have to do to make the EIC actually really work. And that shows you why actually CEIC is such a unique machine to keep you on top of science and technology development for collider experiments. So the thing which I find most impressive is actually this crossing angle and then the crab cavities. And I will explain you why we do this. So we want to have very, very high luminosity. And to do this, you have to bring your focusing elements of the machine as close as possible to the interaction region, to the IP. And you do this if you have a crossing angle, because it's clearly you get more space between the two beams, so you can bring them closer. And it has the other advantage because electrons create synchrotron radiation if they go through dipoles, because you don't need a separation dipole, you have basically no synchrotron radiation. But now look to this picture I have here with the overlap. The beams overlap only to 50%. So a stupid idea to do this because you actually lose luminosity. But we are very smart. We introduce what we call trap cavities, which sit here. They give a kick to the particles inside the bunch and rotate them so that they kind of don't come in with this angle anymore, but overlap to 100%. And then we get fully back our luminosity. This is the first time this gets realized, the LHC, and the further machines are actually very interested in this, and that will be the first machine which does this. So you get high luminosity, without this disadvantage of high backgrounds inside your experiment. And that brings me actually to the experiment. So we are not yet having a Lego model for it, but we are getting there. So the experiment is also kind of really developing very well. We have an enormous amount of effort made in the last years on the experimental program. We started with a call of expressions of interest in May 2020. Then, because we got extremely good feedback from all around the world, we launched a call for detector proposals in March 21. They were due in December 2021. Then a high-level committee took a decision for the baseline. And then since spring 2022, we actually in a process to consolidate the two big proposals which we received, ECHE and ASINA. We formed the official EIC project collaboration, EPIC, in July 2022. And now we have a charter of the collaboration. We launched a research review board for the ones for you which are familiar with the LHC. That is very common. And then we have made just now the remaining technology choices for the detector. All of this, as we could not come to Brazil for Poetic, we were busy doing a yellow report which actually described how the science requirements flow down onto the detector concept. So we have a large worldwide interest in EIC physics. We have a user group which was formed in 2016, which now has basically 1,400 collaborators all around the world, which you can see here with experimentalists, theorists, and accelerator scientists. It has been growing very fast, but we really would like to, and I have been on a couple of conferences in South America, we would love to welcome more collaborators from Brazil and South America overall. And so if you're interested, I have sign-up sheets. Come and see me. I think it would be really, really very nice if we could get more collaborators. The EPIC collaboration, you see here some information. Again, distribution around the world, 160 institutions. Unfortunately, right now we have nobody from Brazil or South America, and we hope really that this changes very rapidly. So here you see a rendering of the detector, actually, and I will go in a little bit more detail where we are. So the tracking detectors are actually, we have monolithic pixel detectors, which ITS3, actually it's a collaboration with Alice to develop this for the microvertex detector, but then the disks and the Sagitta layers based on ATS3 is a first, which is done for EPIC. And we augment this kind of high resolution silicon tracking with multi-pattern gas detectors, which sit at the larger radii, and that is particularly because then you don't need any more the high resolution, and also it is cheaper. Then we have calorimetry. We have coverage of electromagnetic and calorimetry, the same as actually the tracking detectors. So we have the colorimeters kind of electromagnetic. We have in the forward direction, we have a lead tungsten colorimeter, which has actually really a resolution of 1/(-) because of the crystal use. And we read it out with SciPMs, which will be the first time ever to do this. In the barrel, we have a very interesting electromagnetic colorimeter, which has an imaging part where we insert maps detectors in a LED sci-fi kind of matrix. And then we have the sampling part, which is all LED sci-fi. And then in the forward direction, we have a very high resolution hadron colorimeter. We aim for 50%, which follows what is done for the ILC. So the Callis, we have silicon PMs embedded in scintillator, and then we have a very high longitudinal segmentation. And in front of this, we have an electromagnetic colorimeter, which is a tungsten powder scintillating fiber kind of matrix. What is very important is particle ID, because I told you that we really want to kind of in very detail map out pattern distribution functions, but really take the flavor. And for this, we need really to identify pions, kaons, and proton on track level. And for this, we need actually several technologies, because we have to span a wide rapidity range. And with this wide rapidity range, we have to span a wide momentum range for basically something like 200 MeV to something like 60 to 80 GeV. And you cannot do that with one technology. This is why actually we have several PID detectors, again, spanning the whole rapidity range of the detector of -4 to 4. So in the forward hadron direction, we use actually dual radiator ridge, where we have aerogel and a C2FS gas as radiators. And then the photon matrix, again, something which is very new for EPIC, is read out with SciPMs, hasn't done before. In the barrel, we use a Dirk, which is based on the Dirk bars, and then we read it out with MCPMTs, and we reach then pion-kaon separation to 6 GeV. And in the backward direction, we use again a ridge, which is based on aerogel as a radiator, but has another new feature. We use LAPPDs as photon sensors, and we do this because they provide us not only the photon detection, but they provide us also actually with time of flight, because they have this very good resolution. And all of this is augmented by time of flight, which we use ACL guts, which give us 20 to 35 picoseconds. And again, it's the first time that is used in a collider detector. The electronics which we are doing is also kind of very interesting, because we will use, and I show you that on the next, a streaming readout. We have 23 different detector technologies. And of course, we cannot use for each of these detectors a different ASIC. So we need to kind of really find common grounds for them. And you see here, depending on the detector, what type of ASICs. And for the multi-pattern gas detectors, we use a SALSA, which is actually a development which is done here in Brazil, in Sao Paulo. And we are very happy actually that we can utilize this detector. And then, so the electronics is very close to the detector, but then we go to streaming architecture, not like the LHC, where that is implemented as an afterthought now. We really do that from the beginning. We integrate AI and ML as close as possible to the detector, so that we have a cognizant detector, and basically it talks to us and says, look, I need a new calibration for my tracker. And then we kind of stream all the data out, no trigger. So we have the highest flexibility for physics analysis possible. Just to give you a little bit of a feel how all this detector and the accelerator comes together. Here you see a rendering of the interaction region, and you see it's super busy. So you have the main detector, you have the high focusing magnets, you have then, here you split the electrons and the hadrons off, the same in the other direction, and you have running behind the detector the rapid cycling synchrotron, which is the injection, as I said earlier, into the electron. So every centimeter actually counts that you can integrate everything, and it is a big engineering challenge. We have a lot of physics which needs detection of particles with much smaller scattering angles than we have in the main detector. So this DVCS, as I said, diffraction. We want to see incoherent shape psi production for on a deuterium to basically see is there a difference between a bound proton and a neutron and a free one, meson structure, and then also saturation where we want to do this. And all of these particles need to be detected in detectors which get integrated along the beamline. And they sit basically here in the outgoing hadron beam direction. You have the magnets, you integrate them in the magnets and in the beam vacuum so that you can actually really cover this very small angles. And that is something which is very important to integrate in from the beginning into the lattice of the machine. And we are making a huge effort to do this. So here, it's an example actually how well we can suppress incoherent production for shape psi with the current machine design. So we are coming actually really close to the minima. We are still working to improve this. The beam pipe design is absolutely crucial for this. And we hope that actually we really get that we can do there, and then we can do this extremely nice imaging of nuclei like gold. The far backward detectors sitting in the outgoing electron direction, the most important one is the luminosity detector. We want to measure luminosities to better than 1%, and also relative luminosities. That means sorted with the spin direction, because that is crucial for the physics, as the spin asymmetries are in the order of 10 to the minus 4. And so you need to know the relative luminosity per spin state better than this. So now the EIC project. So that is what we do a lot, sit around the table and do paperwork. So here you see actually where we are. So what you see here is a typical timeline of a project in the US. You probably have heard we have these critical decisions where we have several of them. So you have CD0, which is basically the government acknowledges that there is a need for a new facility. Then you go to CD1, which is basically the cost range gets set. You set the scope of the machine. Then you go to CD2, which is the full performance baseline. So then you have really pinned down what you are building. CD3 is start of construction, and CD4 is start of operations. So the EIC project has received CD1 in June 2021, and we will go through the review process in November for CD3A. That is very interesting because that gives you permission to buy and start construction for long lead procurements. Long lead procurements are things which need a long time to fabricate, or you have problems with your vendor base and things like this. But that is basically a start of construction. And then we do CD2 and CD3 have been combined to spring 2020 to January 2025. And then in April 2025, we hope we can start construction. And in June 2025, that is where actually also RIG starts concluding its operation. And we really then kind of take over the tunnel and make all the modifications. And then the early start of operations will hopefully be April 2031. We have been extremely lucky because, you know, funding in the US can be pretty wavy. We have been extremely lucky that we received actually basically 140 million with the Inflation Reduction Act. So this counts towards the whole funding, which is 2.5 billion, which we need for the machine. So with this money, having it early, what it happens is that we basically have a technical driven schedule to CD3 to start off construction. And with that, I come to my end. So the takeaway message is we can build EIC now. And why is this? Because all the stars align. We have actually the support from the series to actually ask these questions and can answer them if we provide the data. We have the technologies for the detector to build actually a detector which can make the measurements which we need to do answer these big questions about the spin, the structure of the proton, and so on. But most importantly, I think, is that the accelerator technology has really made so many advances that we can build an EIC which provides us absolutely everything which we need to do these measurements. And so after the EIC, hopefully, we will not only see anymore the tip of the iceberg, how a proton, a neutron, and nuclei are looking, but we really see the full depths and understand how visible matter is made of. And so let's get to work. Join us. We need absolutely everybody. And here are our links to the jobs at the EIC. And we have many. We have at the moment, I think, something like 80 jobs open. So if you have engineers, postdocs, experimentalists, theorists, please join us. Thank you.
Thank you, Elke. As with the project, hopefully,
Yeah.
we finished on time, under budget.
Exactly.
3 seconds to go. So I think EIC is in good hands here. So let me open the session, the talk for questions or comments. Yes, right there behind you.
This is a bit of a far-future question, but a lot of your motivations have to do with comparing to heavy iron conditions. You know, efficient state small systems.
Not necessarily, but yeah.
PA, not just the heavy iron conditions, sort of the hardware conditions.
Yeah.
Is there going to be, but of course, when the EIC will open, RIC will be closed. And the energies are similar, but they're not quite the same.
Very close.
The previous RIC data, these comparisons will be done using previous RIC data, or at the horizon, there is going to be PA collisions compared to PA collisions.
No, we cannot continue any kind of AA or PA collisions because we take out one of the machines. So we keep only what we call the yellow ring, and the blue ring basically will be dismounted. And the reason also is, let me quickly, I think I don't have too many overlays. Yeah, so it can be seen here. You see, you have the electrons, you have the protons, and the interaction region will be very, very different. You would need to have the other beam going part here. You can never collide at the same moment, because then you would have 3 beams coming in, and that is undoable. So RIC will not go back to anything which is hadron interactions. It will be an electron-proton machine, and it will be EIC and not RIC.
I saw you wanted to raise a hand. Did you have a raised hand? Any other comment or question? We have enough time. Yes.
A comment and a question.
Yeah.
Yes, so the first comments, so you mentioned the possible connection between GPDs and the initial stages of heavy ion collisions.
No, I did not. What I was saying is that so here, what I'm saying is we need to do imaging of the proton to know how it looks like, so that we can put it into, for example, calculations like Heikki and Björn do for this understanding the ridge. And of course, these calculations are done in a hydro picture. They introduce these fluctuations of, and the fluctuations and the imaging, so how the 3D picture can look like, you can do via this, you measure the cross-section, so you Fourier transform it, you get the spatial distribution. And even in the proton, you can measure the incoherent part as well, and that gives you also the fluctuation. I don't need GPDs for this at all, 0. I only, because for all of this imaging part, I don't need GPDs, because the GPDs actually give me only overall normalization. I can do this really by measuring cross-section and Fourier transform, because as we know, we cannot extract GPDs because we don't measure the full phase space. So this is a thing where you don't need GPDs at all.
Okay, I say so because we had a meeting in Paris recently
Yep.
two communities talking together. And the question was, can we learn something from GPTs that can be used for the initial, understand the initial stage of
Yeah.
high energy?
Yeah.
And came out that it was clear that GPTs get essentially the average of the whole
Yes,
configuration.
absolutely.
Access to the situation, which is needed for this.
Yes, yes, absolutely. GPDs don't give you this. It's also here. So this is, that gives you the source distribution, and you get the average of source distribution. And then if you look to the incoherent, meaning that your proton stays intact, but your gold breaks up, then you get actually the fluctuations of exactly how this average distribution looks like. Yes, I completely agree.
You have a question?
So the question
Yeah.
is about the craft technology. It's
Yes.
interesting. Has it been realized in a way or another?
No. So yes and no. There is at the KEC facility, so Bell 2, they have been using, but they do only 1 millirad. We do 25 millirad, and actually at the second detector, even 35 millirad. So this type of crab crossing has not been realized anywhere in the world. So it's very new. The LHC at the moment collides on the micron angle, 100 microns. They want to go to 2 millirad for a later stage. And that's actually something they are waiting for, that we really put it in and realize it.
Other question? Yes.
Yeah. Yeah.
Just trying to see, there are other fundamental questions like color confinement
Yes.
in QCD
Yes.
and the mass generation mechanism.
Yes.
How would they be addressed, or how can we see how they contribute towards having
So-
this three-dimensional
Yes.
image of
So confinement is, of course, a question which is very, very tricky, and the EIC will not answer confinement. Because, but one of the things, of course, is if we have really 3D imaging and we see how the gluons are distributed, which of course holds the protons inside the, holds the quarks inside the proton and so on, it can give us some idea about confinement and maybe some things, but we will not answer confinement. If it comes to the mass, I have some in my backup. So we can do measurements, which one of them is the anomaly, which is one of the contributions to the mass of the proton. But you know, the mass of the proton is as complicated as the spin of the proton, because you have different decompositions. And I don't know, Cedric, are you talking about the mass? Okay. So we can measure this one, and we can also measure the Sullivan process on pions and kaons. And that, of course, gives you an information on how different the gluon content of pions and kaons is relative to each other. And that can give you, again, an information on how the gluons can contribute to the mass through its interaction and the energy. But again, the EIC will not disentangle the mass fully, because it is a theoretical problem. Many of the components to the mass, we can only make contributions to very specific parts of the mass.
You still talk about 10 to the 33 to 10 to the 34.
Yes.
When will it be 10 to the 34?
So as I can talk about that as well. So all machines which have been a kind of built have a commissioning time. And the 10 to the 34 will be probably something like 3 or 4 years after the start of the machine. Because you have to kind of bring on the polarity. You have a lot of things to commission. The machine is very complicated. You have to commission polarization. A very long process. Rick is the only collider which has been polarized, and I can tell you it is a struggle every run. So that takes time to, So if you want to have absolutely everything, high polarization, high luminosity, and so on, it will be 4 or 5 years into the machine.
Are there any outstanding problems that aren't solved?
So as I just showed you, we need to commission crab cavities. We need to commission crossing angle. We need a strong hadron cooling.
I'll take that as yes.
Yes. That's why I'm saying it is not a machine which you turn on and it works. Sorry to say, it's not fixed target. It is so much more complicated. And let me just go to this one picture. All of this is new. It's new technology on a collider. Because of the small bunch spacing of 10 nanoseconds, we need kickers here, which the LHC doesn't have, with the rise time and so on. So we have to develop all of this. So this is, I sometimes call it the summary of the miracles which all have to happen, that the EIC performs to its absolute super, and it will take time, clearly.
All right, let's go.
More general picture on what you said. So EIC will be able to know in details the gloom distribution, the quark distribution, but how we integrate all that in a single picture of the proton?
So after CEIC, I think, or not after, as the EIC moves along, we will really understand how a proton looks like. And not only collinear, but also how the quarks are distributed in space, whether spatial, and how it's transverse. And at the end, it comes basically together that we can measure these Wigner distributions. And I'm sometimes referring to them as the QCD map of protons. So it's basically, it's like you have like a human body where you measure your things, and so you will really understand how that happens. And then the really cool thing is you take these protons and put it in nuclei, and then you will know, is there a difference whether you have a free or a bound nucleus. And the first thing is to make very precise measurements on deuterium, because that is the simplest state of a bound. And because we have these detectors in the forward direction, we can really kind of check, did we scatter in a deuterium on the proton or on the neutron? And then see what really happens. So you get really a full picture about the visible matter all around us.
You have not mentioned them specifically, but I think it's part of the program of the EIC to measure the pion and kaon PDFs.
Yes,
Yeah,
that is a Sullivan process.
So which range in X and Q square you are more or less expected to cover?
So that depends on how much you want to tack at the forward direction. You will not be able to go to the, if you want to do a good measurement, did I have? I think I did. Let me go to the Q square plane. Somewhere I had a Q square plane of EIC, but okay. Probably to 10 to the minus 3 or something like this. 10 to the minus 3 with high precision.
Any other question or comment for Ellen? If not, let's thank her for a very comprehensive. And now we go to the next talk, which will be with Lawson, who will tell us what we can learn from light ions.
Test. Yeah, I think I should be fine. Can you put it full screen, please? Okay, thank you. All right, so thanks to the organizers for inviting me, and thank you to Elke for giving such a wonderful introduction. Does a lot of the groundwork, right? I'm going to talk about a specific subset of the, let's say, EIC program, but that covers a lot of the physics objectives of the EIC program. That being light ions, right? So I'm going to try to give somewhat of an overview of the opportunities that we have with light ions, some of the new things that we can do with them specifically with EIC that haven't been possible at other facilities. Okay, the back and forth isn't. Okay, it's working now, thank you. All right, so let me start with the fact, why are light ions interesting, right? So with doing processes with light ions, we can actually address an essential part of the EIC program, right? So I'm going to go more in detail on the next slide, but we can use light ions to access nucleon structure, right? We can, since they're a bound system, we can look at the effect of nuclear interactions on PDF properties. We can do nuclear tomography if we do exclusive processes, coherent processes on nuclei, and we can also look at coherent phenomena. On top of that, light ions have specific unique features, right? Light ions have spin, right? On top of that, the lightest ions have different spins. Think of helium-3 has spin 1/2, helium-4 spin 0, deuterium has spin 1. Okay, so it gives us access to different spins. And you can polarize them using the EIC. So we can use them to look at specific polarized observables. If we have nuclear targets, we can break them up. Okay, we'll see with the EIC detector, and more specifically the far-forward detector, that allows to do specific breakup measurements. So we can measure particles that originate from the breakup of a light ion. That gives us access to specific observables. On top of that, from the theory side, from first principle calculations in low energy nuclear theory, we have a pretty good idea of their nuclear structure, and that is also something that we need, right, to describe the initial nuclear state and when we try to model these processes. So at the bottom line, if you look at these processes with light ions, we're somewhat at the intersection of two communities, right? On the one hand, you have your high energy probe, right, the virtual photon that interacts with some constituent of your light ion, a quark, a gluon. So that is definitely a high energy scattering process, right, just as an EP. But on the other hand, we have to deal with the initial nuclear state, which is a low energy nuclear probe. Okay. Moreover, of course, there's been a lot of work, right, both from the theoretical and the experimental side on these processes with light ions, but there's still a lot of things that we are left to explore that we haven't done that we can do with EIC. So, okay, so a bit more in detail, what specific parts of the EIC program can we address using light ions? So of course, light ions are bound systems of protons and neutrons. And if you want to do imaging, right, or you want to get to the quark-gluon structure of the nucleon, you don't have enough just with doing EP measurements, right? If you measure PDF, GPD, TMD, it's a weighted average, right, of flavors, different flavors that you're measuring. If you just measure the proton, you don't have enough, so you need additional observables. One of that is doing measurements on the neutron. Of course, we do not have free neutrons, so we use light ions. if you combine then proton and neutron data, you can do flavor decomposition, right, of PDFs, TMDs, GPDs. You can also separate the isosinglet and the isovector structure. You can look at the QCD evolution. You can look at the structure of the nucleon C using all of that. Then, of course, light ions are bound nuclear systems. And you're also very much interested in what is the influence of these nuclear interactions on protonic properties. We know they're there, right, since the first measurements of the EMC effect. But we still don't know much about their dynamical origins, right, how they are related to certain nuclear configurations. Also, what is the origin of the nuclear force, right, the QCD origin of that at very small distances, right? So we know at large distance, it's 1 pi exchange and so on, these things. But what it is at very short distances, that's more of an unsolved issue. Then there's certain observables that are distributions that only exist for nuclei, right? So you can have gluonic distributions that are impossible in a proton that do exist, for instance, in higher spin targets, spin 1 and higher. That give you observables that also connect different nucleons in the nuclei. Moreover, we can also look at coherence and saturation effects in these light nuclei. Okay, so a lot of that is obviously being done on heavy nuclei, but that doesn't mean we can look at it on lighter targets. The last thing is we can also try to image nuclear bound states and their quark and gluon degrees of freedom. Right? And with imaging, I mean going to the GPD picture, right? And for that, one has to do coherent exclusive reactions. So that means detecting an unbroken light nucleus, like a deuterium, helium, right, in the final state. So then we could image quark and gluon degrees of freedom in nuclei, but for instance, also look at, because we know that lighter nuclei also have certain cluster properties, right? So if you think of beryllium-9, which has 12 us and a neutron, so we can also try to make that connection between the clustering and the nuclear degrees of freedom to make the connection with the fundamental degrees of freedom. Now, a common theme in all of these processes is that ideally you want some sort of control over the nuclear configurations that you're probing, okay? So if you want to probe neutron structure, ideally you want to probe a free neutron, right? You want to get rid of any sort of nuclear effect that complicates the extraction of the quark or gluon properties that you're trying to extract from your neutron. So that's one, let's say, issue that you can try to address here, right? So if you do an inclusive measurement, you're going to average over all possible configurations of your initial nucleus, right? So then the question is, can we go beyond that? And I'll show you some of that. Here, if you want to study the influence of nuclear interactions on your quark properties or study the short-range parts of the nuclear force, you want to have some sort of idea of what nuclear configurations are you probing, right? Is it two nucleons far away from each other, closer together? Are you probing low density, high density? So you want to constrain the initial state to some degree. Of course, here, if you do imaging, you need coherent processes. Then you want to be sure that you're detecting unbroken, right, a coherent state in the final state. So here, you want nothing, well, let's say, you want an intact light nucleus in the final state. So again, you need to control that nucleus in the final state. Okay, so to do all of that, to have control of your nuclear state, we of course have our detectors, right? So Aka did a nice overview of that. And she mentioned in one of her slides that the EIC project, or the interaction region here, which has the EPIC detector, has these set of far-forward detectors built in, right? So these go, as you can see here, up to 40 meters, right, away from the interaction point where the EPIC detector is. You have these set of detectors. So this is a very complicated design and engineering challenge, right? Because you have these beam pies, you have the magnets, and you want to put these detectors as close as possible, right? So this is very complicated. And of course, this is useful, as Alka already mentioned, right? Across the whole EIC program. And exclusive reactions, right? On EP, you want to detect your proton. An exclusive diffraction, right? Coherent, incoherent, inclusive diffraction. You also want to detect proton or breakup products of heavy nuclei. If you want to study EP target fragmentation, the Sullivan process, if you want to study pion and cane structure, you're going to detect a neutron or a lambda in the final state. For light ions here, these forward detectors are being used to measure certain breakup processes. So you're going to try and detect nucleons that originated from your nucleus. Or in the case of a coherent process, you want to detect your intact nucleus, right, in that final state. So if you measure products from that breakup process, we also use a lot the word tagging, right? So you tag some sort of a particle in the final state. So that's something that will come back. And maybe a little bit, right? So I don't have many details here, but there's a set of detectors here. So if I go from nearest to the detector, you have and inside the dipole magnets, you have the B0 spectrometer, right? And then you have off-momentum detectors here, the Roman pods, right? So which are used for charged particles, as close as possible to the beam, and then the ZDC here, 0-degree calorimeter. So this is used to detect neutral particles, such as neutrons and photons. Okay, so ideally, EIC will have 2 detectors, right? And there's also opportunity if in the second IR with a second detector, right? It will also come with a second set of forward detectors to have a certain degree of complementarity here. Because obviously, because of this whole design complications, right? It's not possible to cover all of the phase space that you want. Okay? So that's something that we also need to deal with. All right, that's from the experimental side. Then from the theory side, if we deal with high energy scattering of nuclei, how do we typically deal with this, right? So this already sort of introduced, right? But we're at the interplay of 2 different scales, right? So on the one hand, yes, we have our high energy electron, which emits a virtual photon and has a high energy scattering with some constituent of our target, in our case being a light nucleus. And in high energy scattering, we usually do this on the light front, right? So your virtual photon probes your target, here being the nucleus, at a fixed light cone time. So, and light cone time, we use x plus, right? Which is the sum of your time and your longitudinal coordinate, where the z-axis is along your virtual photon directions. Once we do that, right, so here, this is being probed at fixed x plus, we can separate 2 scales, right? So we can introduce intermediate states here. And what we'll do is we will separate the scales of the initial state from the scale of the high energy scattering here. And we can do that using light front quantization and these QCD factorization theorems that were also mentioned in the first talk. So for the top part, if we describe these processes on nuclear targets, the hard scattering processes, we do just the same thing as in EP processes, right? So we use QCD factorization theorems. We write our cross-sections with structure functions that depend on PDFs or TMDs, GPDs, and so on in more complicated processes. Then if you look at the bottom part, this is where the nuclear input goes in, right? And if you do this on the light front, what you get are certain momentum distributions, spectral functions, right? Just as we know from low-energy nuclear physics, but slightly different because they're being probed or being formulated at fixed light front time. So depending on the final state here, right? So if it's a process where you tag additional particles, right, you will have specific overlap functions of this nuclei with a certain final state, right? So this framework is known on the light front since, you know, quite a few decades. People use it. It's well used for the deuterium. It gets quite technical if you really want to do it rigorously for more heavier nuclei, well, heavier light nuclei. So let's say beyond A equal 3, 4. But we know how to do it. It's technical, but we know how to do it. Let me think. Okay, I'll get more to that in a minute, probably on the next slide. In the end, what happens if you do it for the, let's say, the most simple type of process where maybe you detect an additional particle, but for the moment we ignore any sort of final state interactions. So this is what we would call the impulse approximation. You can formulate a cross-section with some nuclear structure function, which can write as a product, right? And that obviously reflects the separation of these two things. So on the one hand, you will have some nucleon structure function, right, where the PDFs, GPDs, TMDs can enter, that depend on kinematic variables of this moving nucleon, right? So it's not just, it's not the Bjork index that you get from your electron kinematics. It's being modified because of the nuclear motion. And then it's being multiplied by some sort of a spectral function momentum distribution that depends on these light cone variables. So alpha will come back a few times. So alpha p in this case would be the longitudinal plus momentum fraction of this proton relative to the deuterium. Okay. All right, about the nuclear initial state. So luckily, we have a very active, large, low-energy nuclear physics community across the world that these days are being able to do fantastic first principle non-relativistic calculations for not only light ions, but these days up to nuclei like carbon. So in a lot of these cases, they use effective field theories, right? Chiral perturbation theory based. And they use control expansions. So they formulate all the 2 nucleon, 3 nucleon, and so on forces in certain orders, calculate all the diagrams. Based on that, they build potentials, and they put that into the nuclear many-body problem. Okay, there's a whole variety of methods, right? People use no-core Shen model, Green's function model, Carnot lattice effective field theories. But in the end, this is one example, right? So from a few years ago, from the Lentic collaboration, which has institutions worldwide. And there you see, right, based on chiral EFT, so with potentials including to N2LO, that they're able to describe here, it's the ground state binding energies, basically, right, up to carbon-12 with very high precision, right? And there's a very nice agreement between theory and experiment. So right now, if you do this high energy, right, for instance, for the deuterium, we do this on the light front. What happens is at low momenta, we match our light front momentum distributions to these, let's say, realistic deuterium wave functions that are around. So in the end, there's still some matching going on, right? So ideally, you could take the same tools, but start again, right, from light front quantization and do the whole exercise again. So that's something that, at least from our perspective, is where a lot of progress can still be made, and also an opportunity to involve the low energy nuclear community. Okay, so now I want to go step by step over some of the processes, right, that we can look at using light ions, and I'm going to start with how we can measure neutron structure. Okay, so obviously the simplest process that we can do is inclusive DIS. Right? So we scatter the electron, we detect the scattered electron, and that's all there is, right? We do not detect any other final state particles. So obviously this, if we do this, we measure neutron PDFs, right? Combined with proton PDFs, we can then do flavor separation, we can look at singlet, isosinglet, isovector contributions, and so on. We can use different light ions for that, right? So the simplest light ion would be the deuteron, just a neutron-proton bound system, but we can also use helium-3 or even triton, okay? So in this case, inclusive DIS, from the theoretical point, it has its advantages and disadvantages, right? The advantages, it's very simple. There are no hadronic final state interaction effects, right? So it's, you can use completeness in the final state. You can compare, of course, between these different measurements, right? Because we have to deal, right? That's a downside. We have to deal with nuclear effects, right? You're averaging over all the possible initial state nuclear configurations. So to get some idea from that, right? You can compare the neutron that you extract from helium-3 with the proton that you extract from tritium, right? So these are mirror nuclei, right? So that gives you some constraints. And of course, the proton you get from tritium, you can compare to the free proton, right? To get some idea of nuclear effects. Also, within helium-3 and deuteron, right, we can compare neutron extractions. Okay, because it's inclusive scattering, right? In the end, the uncertainties will be limited to nuclear structure effects, right? There's nuclear binding, you have Fermi motion, the nucleons are moving inside the nucleus. There are possible non-nucleonic degrees of freedom, right? So the deuteron can have a delta-delta configuration, for instance. Helium-3 as well can have components that have a delta excited states in them. So these are all things that you would need to take into account. So if you want to aim for precision, which is something that we want to do with EIC, we can look at other tools, right, that go beyond some of these limitations. And then one of the things that we can do using these far-forward detectors is that we can measure the breakup, right, or try to measure what we call a spectator and tag this particle in the final state. So in this case, I'm going to start with the discussion for this on the deuteron, right? So which is a bound proton-neutron system. So for the deuteron, if you want to measure neutron structure, right? So the hard scattering will happen on the neutron. What we will do is we will tag the proton with these far-forward detectors. So doing this with the deuteron, and I'll show some helium-3 discussion later, but doing this with the deuteron has certain specific advantages. We only have 2 nucleons inside the deuteron. Okay, so if you detect this one in the final state with a momentum that is quite slow relative to the center of mass momentum of your deuteron, you're quite sure that your deep inelastic scattering event has happened on the neutron. Okay, that there's only one possibility. What you do by measuring this momentum is that you select your deuteron initial state in a certain configuration. Okay, so if you detect this at low momenta, you're going to measure or you're going to probe a deuteron where the 2 nucleons are relatively far apart. Right? If they're far apart, the nuclear corrections should become smaller. On the other hand, if you're more interested in these nuclear, the size of nuclear effects or what the nuclear effects can cause in terms of modifications on your quark and gluon structure, you're going to want to measure at much higher momenta. Right? If you measure at higher momenta, you're more squeezing your deuteron, looking at higher density or higher virtuality, how you want to look at it, configurations, and you can try to match the effects to a specific configuration of your initial state. Of course, once you start detecting particles here, you have to also worry about final state interactions because this nucleon that you detect here can reinteract with whatever products that were being generated or formed in the hard scattering here. So that's something that we have to address in the formalism, right, in the calculation. Now, in terms of neutron protonic structure, which is the focus right now, there's one advantage, and that is if you extrapolate your measurements here towards the momentum where this neutron here goes on shell, you actually get rid of any additional diagrams or higher order diagrams, right? So these would include final state interactions and so on. So that's something very nice. Of course, you need to do an extrapolation, and you need to do an extrapolation to the point where this neutron becomes on shell. To do that, you have to actually go into the unphysical region, right? This is not possible, right? If this particle is on shell, you cannot go to the on-shell pole here. Luckily, one advantage of the deuteron is that it's a very loosely bound system, right? The binding energy is 2 MeV compared to the 2 GeV mass, so it's very small. And the actual extrapolation length that you have to do is very small, and I'll show some of that on the next slides. So compared to helium-3, right, you can do similar things, and I'll show some of that, but helium-3 gets theoretically much more complicated. So that's, at least from the theory side, a disadvantage. Okay, these tagging processes have been measured already, right, at existing facilities. So Jefferson Lab has measured this in the 6GeV era with the bonus and the deep experiments. And right now, they have several experiments that have already happened, that will happen. But it's very challenging in fixed target, right? Especially if you want to measure at small momenta, right, which is useful to do this extrapolation. It's very hard to detect these slow-moving nucleons and fixed targets, right? For instance, in class in Jefferson Lab, they have to actually put in an additional detector specifically for that purpose. In a collider, everything is still moving forward, right? So you have your deuteron beam, right, which is like 100 GeV per nucleon. right? And if you detect a proton here, it will still be moving roughly with half of that B momentum forward. Okay. So that's where EIC comes into play, right? It makes things much more easier to measure these to do these sort of measurements. Of course, then there's no free lunch, right? Downside is it needs a lot more theory input in these calculations of final state interactions and so on. All right, but in the end, doing this tagging, right, can give us access to neutron structure over a wide kinematic range that the EIC has at few % level accuracy. All right, and here are some examples of the unpolarized extrapolation that we can do on the deuteron, right? So what is shown here are reduced cross sections, right, which roughly correspond to the F2 structure function on the deuteron, right? So in the tagged DIS process, right? So it's the same F2 as an inclusive DIS. It's just that you detect an additional proton in the final state. And how that is reflected, you see here, right? So what you're measuring will be the F2 of the neutron at a certain modified x because of the motion of your neutron, right? But the motion of your neutron you control through measuring the kinematics of your detected proton. And then the nuclear effects enter here, and in this case, it's the unpolarized momentum distribution of the deuteron, but on the light front. So that is what is plotted here, right? So it's the cross-section, but with kinematical factors taken out, so it's roughly equivalent to this. And it's being shown as a function of the PT of that proton that you detect, right? So the kinematics, you have two variables, right? So one is the transverse momentum of your proton, the other is the longitudinal momentum fraction. And then here it's being showed for different alpha bins. Okay, here I only show one bin, right? It's around alpha equal to 1, which means that the proton roughly carries a half of the deuteron plus momentum. So this is PT squared, right? So if you take the square root, this is roughly from 100 MeV transverse momentum all the way down to 0, right? So these are simulated data done by Alex Jensch, Kong Tu, and Christian Weiss, published 2 years ago. And to go to the actually on-shell physical point of a free neutron, you have to do this extrapolation, right? So this is because of the deuteron binding energy that it's actually a quite small extrapolation. And this is quite well behaved, so you know, it's a robust extrapolation in this case. Then you can do this for different alpha p bins and look at different x and q squared values, and you see that, you know, we can get to the on-shell neutron structure quite well. And of course, you have some spread here. You know, because of this extrapolation, you're measuring at different alpha bins and so on. All right, that's unpolarized neutron structure. Then, of course, we're interested in spin. That's one of the main goals of EIC. So to measure spin, we also need polarized PDFs. Polarized PDFs means polarized PDFs on the proton, but also on the neutron. So to do that, we can do the same sort of measurements, inclusive but also tagged, but now we will use a double spin asymmetry, right? So we have polarization for both our nuclear targets and our electron beam. And so here I'll be showing polarized deuteron, but I'll also show polarized helium-3 later, which should be possible at EIC as well. So what you have now is you're measuring an asymmetry, right? And in this case, in the numerator, you will measure a double spin asymmetry. So it's a difference of these 4 terms, right? So you flip electron spin, and in this case, it's deuteron, so you can measure +1 and measure -1 polarization. In this case, deuteron has 3 polarization states. For this measurement, we do not need the 0 polarization. Okay? I might show you some other observable where we do use it. Then in the denominator, it's just the sum of all these terms, right? Which means in the case of the deuteron, it's not an unpolarized cross-section because we do not need the 0 polarization mode, right? So it's just the average of the +1 and the -1 polarization. Then you can do the same calculation again, right? So you separate high energy scattering from initial nuclear state. And what you get in the Bjorken limit, so for the asymmetry, and we will average actually over the azimuthal angle of the detected proton, is that you again have this factorization, right, or multiplication. So on the one hand, you will have the asymmetry that you have on your neutron, right, which is inside the deuteron. So this has exactly the same shape as it would have for the proton asymmetry. It's just that it's being measured at this modified x because of the nuclear motion. And then it's being modified by some nuclear factor, right? Which in this case we call D2. And it again depends on the kinematics of the proton that you detect. Okay, and now let me discuss this factor a bit more. So in this case, right, ideally, we want to measure polarized neutron structure. We want to have our neutron as polarized as possible, right? Because they're inside a deuteron, that's not always the case. So some of the neutron polarization is not completely being transferred from your deuteron polarization because of these nuclear effects. So that is what this D2 quantity does, right? That's where your nuclear wave function enters. So again, this depends on the spectator kinematics, right? And in this case, it actually turns out that this has a probabilistic interpretation. So this ratio gives you the amount of neutrons that are polarized inside the polarized deuteron compared to the unpolarized neutrons inside your polarized deuteron. So in a way, it's sort of, you can think of it, if you're used to thinking in terms of TMDs, both the numerator and the denominator here are sort of a TMD of the nucleon inside the deuteron. Okay? Since it's probabilistic, it has bounds between -1 and 1. And it actually turns out if you go to zero transverse momentum, right, which is what we want to do with these extrapolation methods, that this factor is always 1. And it has a clear physical reason for that. It's because if you go to zero transverse momentum, there's no orbital angular momentum, right? And it's exactly the orbital angular momentum. It's the D wave in the deuteron that is able to flip your neutron spin compared to your deuteron spin. Okay, and then if you go to higher momenta, that is what you see happening here, right? So around 300, 400 MeV, the D wave in your deuteron completely dominates, and it causes your neutrons to flip compared to the deuteron polarization, right? So it actually goes to -1. All right, obviously the good news is it's almost 1 at these very small recoil momenta, right? And that means that we can actually use this to extract free neutron polarized quark and gluon structure, right? So these are these asymmetries being extrapolated. Again, here is the on-shell, the kinematical limit, right, of zero momentum. Then you have to do a small extrapolation to get to the on-shell free neutron structure. Okay. Same thing can be done using helium-3 targets, right? And that will be possible earlier in the EIC timeline. And then people have looked at this for this study a few years ago, right? Also in the context of the yellow report. And in this case, they do double spectator tagging, right? So you take a helium-3 target, obviously it has 2 neutrons and a proton. And in this case, you're gonna tag a proton and a neutron to get to the free neutron structure. And they did simulations, right? So the shaded band here is the asymmetry they get from the inclusive measurement or the simulations that they do. And then the black dots is what they get from this tagged measurement. So you see that you actually get a reduced uncertainty here, right? In terms of nuclear effects, one has to be careful here because if you're dealing with 2 tagged spectators, they're actually moving quite slowly relatively to each other, so they can actually have quite huge final state interactions, right? It's like a low energy nuclear system that is moving here. And that wasn't included in this simulation, right? So that's more work to be done from the theory side, let's see. All right, so if we talk about these final state interactions and tagging in the context of EIC, we do have to take them into account, right? And then the question is, what sort of is the dominant dynamics that we have? So it turns out at the X range that you have at the EIC, right, which is what we call intermediate, so 0.1, let's say the higher end of the limit, and then you go down in X, but at the higher end of the X range, the dominant mechanism is that you will have some slow hadrons being produced in the high energy scattering, and those slow hadrons will reinteract with your other nucleons inside your nuclear targets. Okay. So that means to get an idea of this, because not a lot of this is known from data, right? You actually can make use of EP target fragmentation data because you want to know what are these slow hadrons, what are the distributions, right? And momentum and PT and so on. It turns out from data that we have, which is mainly Hera, I believe, that the dominant contribution to this are actually slow protons or slow nucleons, right? That then re-interact with these spectator nucleons inside the nuclear target. So it turns out that actually your final state interactions that we get in these high energy processes on like nuclei at EIC have a lot in common with what we know from quasi-elastic deuterium breakup at intermediate energies. So you have some nucleon moving here at a few hundred MeV, right? And that scatters off another nucleon with similar sort of momentum range. And that's what you see here. So what we know from that is that at low momenta, you get a slight reduction of the cross-section, which peaks at 90 degrees, right? So that is where your final state interaction dominates. If you go to higher momenta, right, of your detected spectator, you actually get larger and larger final state interactions, which peak in the forward region. Okay, the good news is, if you do pole extrapolation to get to this free structure, that the final state interactions always disappear, all right? However, they're there, right, once you go away from the extrapolation point. However, it doesn't affect the extrapolation that much. All right, then I want to move on to nucleon interactions. So one of the questions there is, how do nucleon interactions emerge from QCD, right? So what role does the short range structure of nuclei play? What is the character of the nucleon-nucleon force at very short distances? Right, so there we can try to measure quasi-elastic deuterium breakup at very high relative momenta. People do studies of short-range correlations, right? Multinucleon knockout. All of these are in principle also possible at EIC. Related to that, we want to have an idea of how partonic properties in nuclei are modified by nuclear interactions, right? So what is the EMC effect, right? What is the gluonic EMC effect? What is its Q-squared dependence, isospin dependence, and so on. Also spin-dependent EMC effect, right? That's something that we don't really know much about. GLAB will have a measurement, but obviously here at EIC, we can also do a lot. Okay, so fixed target facilities such as Jefferson Lab have a large program for all these sort of things, but open questions will still remain that can be addressed at EIC. Right? And there are also specific reactions that we can look at EIC that are not possible or very hard to do in fixed target. So one of the things that people have been looking at is this diffractive deuterium breakup. Right? And then they're interested in how gluon density is modified in these measurements on the deuterium compared to the free proton. So in this case, it's again a deuteron, and what they looked at, so this was done by Kong Tu and collaborators, also in the context of the yellow report, is that they look at double spectator tagging. So it's a diffractive high energy process here on the proton, right, or the neutron, and they detect both nucleons in the final state, and you have a J psi produced in the let's say in the high energy process, right? Where here the gluon density then enters. And they simulated this up to momenta, right? So this is the missing momenta. You can think of it's the relative momenta in the initial state of the deuteron. Okay, and they simulated this, and so in principle they should be able to measure this up to relative momenta of 1 GeV. Okay, and so that you can look at how this quantity then, right, which is related to the gluon density, will be modified in these processes. And they did that by, introducing some modifications to this quantity here for the bound proton inside deuteron compared to the free proton case. They did Fourier transforms, right, of these distributions, and then this is the sort of effect that they get, right, in these deuteron measurements with double tagging, right, which in principle they think should be observable at EIC. A few years earlier, Matt Sivert, Jerry Miller, and Raju did a theoretical study of a sort of related process. So this is also diffractive J psi production on a deuteron, but they were looking at these two nucleons here with very high PT. Okay, so relative PT on the order of a GeV scale. And in that case, so their interest was that, yes, you will have some diffractive process, but if there's a very high PT here, you can have actually also the contribution where you're exchanging gluon octet contributions, right? So there's some intermediate state here where after these two gluon interactions, you won't have 2 color singlets, but there will be 2 color octets. And then you have some additional final state interaction to create your 2 nucleons with high PT. And their interest was to sort of, we can use this process to distinguish between these 2 processes, to see like, can we distinguish between like short-range correlation contributions from color octets and color singlets. All right, then in my last few minutes probably, like how many? 1? Half a minute. Okay, let me just quickly talk a little bit about shadowing, right? So what happens at low X, if you do high energy scattering, is that a significant amount of the events that you will have will be diffractive, right? So this would be for EP. So you have some Pomeron sort of exchange, color singlet, and your proton stays a proton, right? The same thing is obviously possible if you do it on nuclear targets. So again, here, case for the deuteron. But then, of course, your diffractive process can happen on each of the nucleons, right? And each of the nucleons has the, if it happens on different nucleons, they have the final state. So you'll have interference, okay? That interference will give you what we call nuclear shadowing. Of course, if you have a final state like this, these 2 nucleons can, again, they're slowly moving, right? There's not much of a momentum transfer here, sorry about that. So you will have final state interactions here, which are, again, a lot like low energy nuclear final state interactions. So these are, again, things that you need to take into account. That has been done in the context of tagging, right? So with these spectator tagged interactions, it turns out the corrections are large, right? So you get effects up to 40% of final state interactions. Keep in mind, these 40% is for the diffractive events, right? Which is a subset of the total amount of events, about 10%. But still, these are things that you need to think about. You can look at shadowing as well in coherent processes, right? So this is coherent J-psi production all helium-4, right? Where we saw these diffractive minima in the previous talks, but the shadowing corrections would actually cause the minima to shift, but also to fill up. And that's sort of the effect that you see here. So that was calculated last year by Vadim Guzey, Matteo Rinaldi, and collaborators, and they actually quantified these effects. So it's actually from the one-body final state interaction corrections, you get a quite significant effect. So you can use that to actually disentangle the dynamics of shadowing. They call it shadowing 1 nucleon at a time by using these nuclear measurements. Okay. So in the end, how it enters here, right, how nuclear structure enters here is that you get sort of K-body form factors entering in the scattering amplitude. Okay, I wanted to discuss also coherent GPDs, so for imaging, but I think I'm out of time. So people are also doing simulations for that. So in principle, it should be possible to extract these charge density both in X and transverse plane, right? For instance, helium-4. So these are studies being done at Orsay and Perugia. They collaborate on that. And I'm going to skip the tensor polarization and state my conclusion. So I showed you some aspects, right? So obviously, there's more I can tell you about. Feel free to ask me questions later on as well. But I showed you that light ions address important parts of the EIC physics program, right? Obviously, we can do inclusive scattering, but wonderful machinery at EIC gives us many opportunities to go beyond that by measuring breakup processes, tagging particles in the final state. We can also look at coherent phenomena with light nuclei, so both to study shadowing, coherent imaging with GPDs of light nuclei. And yeah, all this requires excellent detection capabilities in the far forward region, which we will have, thankfully. All right, thank you.
Thank you very much. All right, we have time for questions and comments. Please raise your hand and step forward. Yeah, go ahead.
How critical is the implicit approximation and how can you test it?
Critical to what? Or,
To the description in the extraction of neutron properties and this kind of stuff. Because you mentioned that it's something that you use, but
I mean, you use it as a first step, right? But then afterwards, you do add the final state interactions, right? So,
okay.
So I don't know.
Yeah, but okay, so but the final state interactions are the nuclear ones.
Yes.
You don't have also the inclusion, for example, or does it include, for example, the extra pair creation that you would have in a relativistic theory, which is also beyond, so the Z-graph, if you wish.
No, but since it's done on the light front,
Yes.
right, in principle, at least in impulse approximation, the Z-graphs
Yes,
drop
but
out.
in reality, you have more than impulse approximation even in the like.
Yeah, but again, so yeah, maybe I should go back. Yeah, maybe here, right? So still, it's the final state interactions will happen down here somewhere. So it's not in the high energy process. So still there, it's not in the final state interactions. You will not have the Z-graphs or anything like that, right? So it's still what you get is your like modified spectral function, momentum distribution, right? Which become like NN T matrix elements, stuff like that. But it's not that the final state interaction affects. It will affect the momentum that enters here into the hard scattering, but it doesn't affect the dynamics of the hard scattering. Maybe that.
Okay. And at the EIC, will you reach the sensitivity where you have to add also the correction from electromagnetism or not?
For
the electromagnetic interactions between, for example, two protons and so on, all this beyond QCD effects.
You mean your radiative corrections?
Yeah, for example. But
yeah, I mean, definitely.
Okay.
So for instance, especially on larger nuclei, right? So in the diffractive processes, people have looked at some of these things, and yeah, they are important effects. So yes, that's something I didn't talk about here, but absolutely.
Yeah, thanks a lot. Maybe related to this, one thing that I didn't quite get is that once you have DIS on the deuteron and tag on the forward proton, cannot that proton originate also from the hard interaction with the neutron or from the neutron remnant? Or how can you tell these apart?
Yes, though in collider kinematics, the separation and rapidity is large enough that, you know, the probability for that proton to originate from this region is small enough. But for instance, at fixed targets, that's something that you see. So Jefferson Lab has measured this up to a momentum of like 400, 500 MeV. Then if you look at the forward region, at least, you know, with the models that I've done work with, there, the standard final state interaction is not able to describe the data. So probably what you're seeing, what you're measuring here, part of it also originates from that region. But again, at EIC, right, let's say the geometry of your collision is quite different, right? You have a much wider rapidity gap between target and current fragmentation regions, so there that sort of contamination should be less of a worry.
Any other question or comment? Yeah.
Wim, you mentioned that gluons may come not only from one nucleon, but from two nucleons. Do you mean that beyond, I mean, the nucleons are overlap and they form this kind of funny configurations with
so
6 quarks?
Maybe
this
I phrased
what
it
you
poorly,
mean, no?
but it's also these sort of effects, right? So wherein at low X, you have Pomeron exchange, but the interaction happens with more than one nucleon. Yeah.
Any other questions or comments?
But that, maybe to come back to your question, but then there are, for instance, in exclusive processes, you could have two gluons attaching to different nucleons, right? And then, okay, you have some color non-singlet state in the intermediate, but those are also things that are possible. right? On beyond this, the single nucleon picture and these sort of things, right? So there definitely that sort of thing is, yeah.
All right, I think we are at the end of this part of the morning session. So we'll break for coffee now and come back at 10:20 at the planned time. So.
So there's a last minute change. The first speaker tomorrow, Victor Gonçalves, caught COVID and he's in isolation. He couldn't come, so we canceled his flight. So what I propose is that we shift all, so Jamal would be talking first tomorrow. We just shift all the talks by 50 minutes. And instead of having the poster session today, I mean, you can still hang your posters, but instead of having the poster session today at the end of a longer afternoon, have it tomorrow since we already have an hour more. Okay? Is that fine? Okay, thank you.
Waiting for you. Nice. Very nice to meet you. Nice to meet you. Be here. Great. We'll be talking more.
How you doing? Hi.
Okay, let's get to our session. If you could have your seats.
Yeah, I haven't seen him for ages.
All right, so we'll have the third talk of this morning session, which will be Tony Thomas, and he'll tell us about from quarks to gluon structure, in protons and nuclei, even going into dark matter. All right, Tony, you're on.
Okay, thank you.
Give you a 10-minute warning.
Thank you. Okay, good. So I have enormous trouble handling switching slides and pointing, so I'll use two, and hopefully that will work. Okay, so I'm going to describe a different way of looking at atomic nuclei from what's become the standard model, if you like, and I hate that term. Anyway, let me explain to you why you should look at nuclear structure a different way. A consequence of looking at nuclear structure from this point of view is that the structure of a bound hadron changes from what it is in free space, and one needs to be able to look for those effects experimentally. And finally, for something different, I'll tell you about a recent result. Okay. So, what is an atomic nucleus? There are two different views of that. There are probably many views, but there are two major views. The first is up the top, and it's really paraphrasing what's been said about the Electron-Ion Collider, although I'm not sure whether the people who said it know the way I interpret it. The reason that you want to build an Electron-Ion Collider, one of them is to study the quark and gluon structure of a nucleus. And that's pretty stupid if the quark and gluon structure of a nucleus is the same as it is for a nucleon. So implicit there is that there's some change in a nucleus. The second is something which is the more traditional view of nuclear structure, considering quarks as in contrast to our modern understanding. Basic degrees of freedom, quarks and gluons, have to be considered only at higher energies. The energies relevant for nuclear physics are a few MeV. This is wrong. Why is it wrong? Well, many of the people who say that should know better, but many of the people who say it weren't born in the 1970s. And so they don't know that using dispersion relations, one learned a lot about the nuclear force. In particular, on the basis of dispersion relations, we know that the intermediate range nuclear force is isoscalar, Lorentz scalar, 0+ quantum numbers, and it's strongly attractive. Any relativistic theory that you build of nuclear structure leads to a mean scalar field of order 3 to 400 MeV or more. That's almost a half the mass of the nucleon. Now, of course, the binding of atomic nuclei is a few MeV, and that's because there's a cancellation between the Lorentz scalar attraction and the Lorentz vector repulsion. But those two forces have a very different effect on the internal structure of a hadron. The scalar field changes the internal dynamics, whereas the time component of a vector field, like the omega, which is the typical way in which that vector repulsion is described, simply shifts the energy of the system. It doesn't change the internal dynamics. That's something that's extremely hard and unnatural for a non-relativistic effective field theory to describe. Of course, you can fit parameters to three-body forces, and you can describe 10 or 11 nuclear levels with 4 three-body force parameters. But is the underlying physics correct? So the approach that I'm describing to you says we take confined quarks, described by a wave function psi. We solve the Dirac equation, and in its initial formulation, this model, which we call the quark-meson coupling model, is based on mesons coupling to confined quarks. So the quarks feel, in addition to being free, they're no longer free inside the hadron, they feel an applied scalar field with a coupling of the sigma field to the quark, and an applied mean vector field with the mean field omega with a coupling of the omega to the quarks. Now the difficulty, and in addition to this, in the MIT bag model, you imply boundary conditions that confine the quarks in a volume. Simple model. The complication is that this sigma field, the strength of the sigma field, depends on the coupling to the nucleon, and that's proportional to the integral of this wave function, psi by psi, over the bag. So the sigma field depends on the quark wave function, and the quark wave function depends on the sigma field, and you have to solve that self-consistently. As a result, the internal structure of the nucleon, in this case, changes. And the net effect is that the coupling to this scalar coupling to the nucleon actually decreases as the strength of the scalar field increases. And so when you solve in nuclear matter for the mean field, the effective mass of a nucleon, you get not just the free mass minus the coupling to the scalar field. G sigma is the calculated sigma nucleon coupling in free space, calculated in terms of the sigma coupling to the underlying quarks. But in addition, there's a term which tends to counter that as the sigma field gets bigger. The internal structure of the nucleon rearranges itself to try to oppose the applied scalar attraction. This is analogous to the electric polarizability, where when you apply an electric field to a hadron, it tries to oppose that applied electric field. So we call this the scalar polarizability, and the bag model, it's about 2.2 times the bag radius. The effect of this change in structure is that when you bring 3 nucleons together in a medium, the internal structure of each of them is modified by the fact that there are other nucleons present. And so the interaction between 3 nucleons is not just the sum of the pairwise interactions, but there's an additional term coming from that change in the internal structure. And it's entirely predicted in terms of the scalar polarizability. And that 3-body force is predicted without any new parameters for the 3 nucleons, a hyperon and 2 nucleons, so 2 hyperons and a nucleon, and so on. I won't talk about neutron stars in this talk, but this means that when you come to higher densities, this theory automatically predicts repulsive 3-body forces, which tend to make it possible to have hyperons in heavy neutron stars. But that's not for today. So how do we apply this to nuclear structure? Well, our first attempt at that was back in 2006. So we take this relativistic theory, where we've solved self-consistently for the mass of the nucleon in a scalar field. From that, we derive a non-relativistic energy density functional with central isoscalar, isovector, effective mass terms, finite size, spin orbit, the usual thing that one finds in Skirm forces for nuclear structure. The only difference, the major difference in this simple approximation to the energy density functional is that the central piece, which goes like the density squared, rho is rho n plus rho p, has higher order terms which are proportional to this scalar polarizability. These higher order terms are the effect of 3-body forces on the energy density functional. And so they're implicit in this energy density functional. So the first application of this to nuclei was 10 years later. It took us some time. The parameters of the model, which are the coupling of the scalar, vector, and rho mesons to the light quarks were constrained so that nuclear matter properties were in a reasonable range. And in addition, with the addition of 2 pairing parameters, this was fit to 106 nuclei across the periodic table. You see, for example, if we look at gadolinium, we have a bunch of isotopes with neutron number between 74 and 100. The super heavies were not part of the fit. So nuclei with Z greater than or equal to 100. If you look at the accuracy one got in that calculation for the super heavies, which were not part of the fit, they were reproduced at about 0.1% accuracy. In comparison with SV min, which doesn't have these higher order terms in the density, it's clearly an improvement. This is the absolute difference between experiment and theory, and the experimental values are about 1,600 to 2,000 MeV binding for these heavy systems. So this is a promising improvement. A later study of super heavies you can find here. I'll show you some recent results in a minute. That initial model was very simple. The way the sigma field was calculated in terms of the density was very approximate. In addition, the Fock terms for the sigma, rho, and omega mesons were included, but not the pion. Those were included in the next step, which we call QMC pi 2. And in addition, we had to introduce a term cubic in the sigma field. The reason for that was without it, the compressibility was too large and we could not reproduce the giant monopole resonances. You see here that the experimental values are reproduced with the addition of this term. If we look at the difference between neutron and proton radii, the predictions are very similar to other theories. It's interesting that the value for lead for the difference between neutron and proton radii is about 0.16. That's still within 2 standard deviations of the P-Rex claim, and very similar to other theories. For calcium-48, it's in agreement with the recent measurement, C-Rex, I think it was called, from JLab. If we look at deformation, the experimental values for the gadolinium isotopes are these black boxes. And you see that this theory, which is the blue triangles, reproduces that very well. There are more improvements that have been added to the model, and now I'll show you results which are the most recent. And most of these are unpublished because, unfortunately, the very brilliant student, Kay Martinez, went back to the Philippines where she has a job and has to teach 30 hours a week. So she also has a 1-year-old baby. So we haven't yet written this work up, but nevertheless, I wanted to show you some of it. The theory has 5 parameters: the mass of the sigma meson, these 3 couplings of the mesons to the light quarks, and the strength of the sigma cube term. From those, we derive a tensor for what's called a tensor interaction in the SCIRM nomenclature. And in addition, we have a pairing interaction, which is derived in the theory. G sigma, for example, is the usual sigma coupling to the nucleon squared over the mass of the sigma squared. Similarly for G rho and G omega. In comparison to this theory, which is derived starting at the quark level with 5 parameters, for example, FRDM has something like 27 parameters, I think. Typical SCIRM forces are of order 16. So let me show you, at the moment, the code we have only does even nuclei. And so there are about 760 of those nuclei. And you see here the deviation between theory and experiment. Light green is good. And you see it's predominantly light green. The deviation between theory and experiment, purple and dark blue, is good. So you see above about 20 or 30 for N and Z, we're extremely good. Across that whole set, the RMS deviation in binding energy is 0.29%, and that's better than anything else, including unit F1. FRDM's the only thing that beats it, which is, of course, purely phenomenological. For charge radii, again, this is more accurate than anything else, 0.5% RMS deviation across these 760 nuclei, and the others are considerably higher than that. For the drip lines, we're not quite as good, but nevertheless, the drip lines are mapped out very well. Of course, they aren't all known. They aren't known in general, but these are predictions which can be tested. For deformation, the percentage, the absolute deviation is given here. Again, purple is good, and you see the deviation between theory and experiment. On average, it's about 28%, and FRDM, which is this theory with 27 parameters designed to do this sort of calculation, is comparable. Everything else is considerably worse. I remind you, all this is with something that derived starting at the quark level with just 5 parameters. We can look at shape coexistence, which is fascinating, unless there's a specific question. You see here, for example, for germanium-64, you have this equal binding energy for oblate and prolate shapes for the nucleus, which is fascinating. That becomes more important when you move to the super heavy region. Our first paper is this one with Morita-san as a collaborator, quite well known for his work in this area, particularly in Japan. This shows for this theory the deviation, again, between theory and experiment, so the binding energy residual. The red points are what you need to look at, and 0 is what you would like. The RMS deviation for the super heavies that are known, so Z equals 100 to 118, is 0.03%. And the nearest is unit F1, which is more than double that deviation. You notice that FRDM, which usually does better than anything else, was not fit in this region, and it starts to deviate as you move away from the region where it was fit. This has led us, as a future project that we intend to pursue, to look at heavier nuclei, so going beyond Z equals 118. That's extremely challenging, as you see here. For example, this is seaborgium, and if we look at the deformation, you see there are multiple minima, and you really have to fix the deformation, minimize the energy, fix the deformation to map out the structure of these nuclei. It's very complicated. I hope I've convinced you that this idea of starting from the theory where the quark structure of the nucleon is modified is not stupid. It can be turned into a quantitative theory of nuclear structure, which is as good as any other. So, it looks a bit like standard Skirm forces, except that there are more complicated density dependence, which is derived from the underlying theory. But underlying this calculation of an energy density function is the prediction that the internal structure of the nucleon is modified. And that's something you need to test. For example, by looking at deep inelastic structure functions or elastic form factors. I'll talk just about deep inelastic scattering, in particular the EMC effect. So this is more than 40 years ago. The deviation of the structure function per nucleon for nuclear matter, in fact, compared with the structure function per nucleon for deuterium. And that's the blue, is more modern. The red was the original excitement from EMC. And that's what we're trying to understand, particularly the fact that in the valence region, there's a drop in the momentum carried by those quarks. Now, back in 1989, 1 year after Guichon originally proposed his first version of the QMC approach, we applied that to these structure functions and showed that we could understand the EMC effect. But it was done in the MIT bag model, and calculating structure functions in the MIT bag model requires a lot of subtlety and cleverness, and it's not an ideal theory to use. So more recently, we've used the NJL model with Wolfgang Benzi and Chloe and others over the last couple of decades. The original work on that generalization was back with Wolfgang Benz 20 years ago. So if we look at the results of those calculations using the same idea, that is self-consistently modifying the structure of the nucleon in medium, but using the NJL model for the structure function of the nucleon, you see for carbon-12, the data for the EMC effect and the calculation. For aluminium-27, again, the data and the calculation. The theory reproduces the unpolarized EMC effect. But in addition, it predicts an effect for a polarized nucleus. And so that's why this is labeled boron-11, because then we have, if boron-11 is polarized, we have a polarized valence proton in boron-11. And you see here that there's a prediction for a strong EMC effect for the spin structure function, both in boron-11 and aluminium-27. Unfortunately, as A goes up, because the spin effect is a 1/A effect, it becomes harder to measure. Here we're dealing with a theory which is based on a mean field treatment of the nucleus. And so a light nucleus is not so good, but nevertheless, we're stuck with what our experimental friends can do. And the proposal is to measure lithium-7. And you see here the calculation for the unpolarized EMC effect for lithium-7, which is fine, and a prediction for the spin-dependent EMC effect. Hopefully, this will be measured soon at Jefferson Lab. I'm not sure what the status of that experiment is, but it's important. It's important because a number of people have become infatuated with the idea that the EMC effect is entirely caused by nucleons in short-range correlations. It's very simple to show, and this is the archive version of a paper that I wrote. It's very easy to see that if the EMC effect is given by short-range correlations, there is no spin EMC effect. It's a simple matter of looking at Clebsch-Gordon coefficients for the tensor force. And so this is an extremely important experiment from that point of view. When we come to talk about gluon structure, which is something that the Electron-Ion Collider can look at, you see here the EMC effect for unpolarized nuclei and the EMC effect for spin in nuclear matter. This is a theorist's calculation, of course, because the spin-dependent structure function for nuclear matter is meaningless, but we can do it as theorists. Obviously, if we're going to have to do it for light nuclei again at the EIC. But you see there is a strong spin-dependent EMC effect for gluons. Sorry, this is the unpolarized EMC effect for gluons. The dashed curve here is the spin-dependent EMC effect for gluons, and the red is for quarks. So there's an important test to be made there at the EIC. Last thing I want to say about the EMC effect. How am I doing for time, Habe? I'm fine. So I wanted to say this work is new, but I think it's very important to find a way to discriminate between the idea that all of the nucleons in a nucleus have their structure modified and this proposal that it's only short-range correlations which modify the structure of a nucleon in a medium. This is taken from the Nature paper of Schmuckler and collaborators. This is a collection of data from a variety of nuclei, all normalized such that by the number of pairs of neutrons and protons involved in short-range correlations. And this is the correction from a free nucleon structure function for a nucleon involved in short-range correlations. Now, it looks mild, doesn't it? The trouble is, this is multiplied by the number of pairs of nucleons in the deuteron involved in short-range correlations. And if you set a minimum momentum for something in short-range correlations at 300 MeV over C, which isn't all that high, that's about 3%. If you divide this by 0.03, you get something like this. And this is what's implied by this interpretation of the EMC effect for the structure function of the modified structure function of nucleons in short-range correlations divided by the free structure function. It's a huge change. Of course, it can't be negative, but it's basically zero between 0.6 and 0.8. In order to see what that might imply, we've taken an ADS QCD model because with that simple, well, it's not so simple, but within that theory, we can have a wave function for the quarks from which we can calculate both the structure functions and the form factors in an almost analytic way. And so the black curve is the free neutron and proton F2. The pink or red curve is that curve multiplied by that factor I showed you for the modification of structure functions in short-range correlations. And the dashed curve is a fit within this simple model to this pink curve, starting with that in the free case and then modifying the wave function to reproduce as well as we could this red band. If you take that same theory and calculate, for example, the electric form factor of the proton, it goes from the black to the dashed curve. That's a reduction of more than a factor of 2 at 1 GeV squared, or if you were measuring the longitudinal cross-section, a factor of 4. I'll leave you to decide whether that's a reasonable thing or not. Finally, let me come to something different, and I just had to talk about this because it's new, it's either exciting or it's nuts, and I'll let you decide. Well, the work is not nuts. Whether the result is correct, that's something we need to find out. We know that we have this mystery in the universe, that there's this, at least our particle physics friends, not us, of course, were so arrogant about how well the standard model worked, right? We could understand everything within the standard model. It turns out that the standard model is only 4% of the universe. And so we had this wonderful understanding of this tiny little bit, but knew nothing about the rest. So the question is, what is this dark matter? And in my country, we have a center which for the next 6 or 7 years is trying to investigate dark matter, just like many people are around the world. And as part of that, there's an underground lab being built in Stawell, which is about halfway between Adelaide. This is a Victorian map, so it shows Melbourne, but it doesn't show Adelaide, but it's about halfway between. This is how you get to it. It's about a half-hour drive underground. That's the lab a few months ago. It looks a lot better now. The idea is to make a repeat of the Dharma Libre experiment, but in the southern hemisphere, so that if the effect they see is background, which is not understood but related to season, we'll be 6 months out of phase, and hopefully we can figure out what's going on in that experiment. But it's basically sodium iodide, very low radioactivity sodium iodide crystals, shielded 1,000 meters underground. Now, as well as the experimentalists who work their guts out, there's a few theorists in this center, and this is part of that theoretical effort. And I want to tell you about it. So the dark photon is a theoretical construct. The idea is we take a boson, which is basically dictated by the UY1 symmetry of the standard model. So it's an additional U1Y boson. It's denoted by the prime, so there's a mass term. And in addition, it couples to the B boson in the standard model. So that's the coupling is given by this strength epsilon. So the parameters of this new beyond the standard model particle are its mass and its mixing parameter, epsilon. When you diagonalize this, you go from the standard model Z, which is called Z bar, to the physical Z. And there's a bunch of corrections. There's a mixing angle, and there's another mixing angle related to epsilon. And in addition, this is the vector coupling to the photon. The couplings of the dark photon, again, involve the coupling to the photon, the vector coupling to the photon, and the vector coupling to the Z. Again, with epsilon W is basically proportional to epsilon, this mixing parameter of the Lagrangian density. This is not very informative, but this is how you calculate the mixing parameter epsilon W and that mixing angle alpha. What we wanted to look at, because with a postdoc there who's doing great work, Xuangong Wang, we'd done an analysis just to see what the effect of a dark photon might be on deep inelastic scattering. And we found basically on a very limited data set that it didn't improve the chi-squared. But we thought, since Wally Melnichuk is spending a year in Adelaide, and we have a very good student, Nick Hunt-Smith, who could work on this, we decided to analyze the world data on deep inelastic scattering, including a dark photon. So in addition to the exchange of a photon and a Z boson, we exchanged this dark photon. Remember, parameterized by its mass and its mixing parameter. So if you play the game, good, yeah. So if you're a good person and you decide there couldn't possibly be such a particle, and so you just ask, how much does including this particle increase chi-squared, and what does that say about what values are not allowed for the dark photon? And if by chance the chi-squared gets below the standard model, you ignore it, then what you get is this exclusion curve. So the blue region is the allowed region, and below that, it's not allowed, okay? Oh, sorry, above it, it's excluded. It's excluded at 3 standard deviations, up here and up here. 2 sigma, 1 sigma, and down in here, it's not excluded by this data. Now, this analysis had a cut on the lowest Q squared for the data of the mass of the charm squared. W squared was greater than 10 GeV squared, and it involved an analysis of over 3,000 fixed target and Hera data. So this is what everyone in particle physics wants to see. There's no new discovery, thank God. We'd be upset if there was something new. And this is the limits for the particle. However, if you take the possibility that such a particle might exist seriously, and you look at the chi-squared per degree of freedom for the data, what you find is that for fixed target, there's an improvement. Now, it's only 0.04 per degree of freedom, but there are close to 1,500 degrees of freedom. That's a significant improvement in chi-squared. Similarly for Hera, neutral current data. Charge current, it gets a bit worse, but there's very little of that, and so on. Altogether, almost 3,300 data points. If you use this analysis and ask, what is the probability that the standard model is correct, given this analysis, then you find the standard model, the best fit to the data, including the dark photon, excludes the standard model at 6.5 standard deviations. Now, this mixing parameter is uncomfortably large. But even down here, where the constraints of electroweak precision observables would say we need to be below here, even at 4 standard deviations, we're excluding the standard model. This shows where the chi-squared improves across the plane of x and q squared. And the red points are where the chi-squared improves most significantly. And you see that it's most significant across the whole range. There's no particular region of x and q squared where the dark photon makes an improvement as opposed to the rest. It basically is everywhere. If you look at the parton distribution functions, and the way these error bands are distributed is by, you make a fit to the data, you then distribute all the data points within their errors and fit again, and you do that 200 times, and this gives you an estimate of what people like to call, what is it? Anyway, basically the posterior. And so we see here that the baseline means no dark photon, the red means with a dark photon, and within errors, the PDFs that you get from the analysis, including the dark photon, are equivalent within errors. Of course, it would be very interesting to do this with more replicas, reduce the errors, and see if, for example, for D over U, where the CDF analysis claimed to be sensitive to that ratio, whether in fact there might be some effect there which could have an influence on the somewhat anomalous CDF value for the W mass. If we ask what are the best fit parameters, then the best fit sits up here. But again, we have values down here with quite reasonably low epsilon at 4 sigma from the minimum, but still much better than the standard model. Now, clearly, this is something that needs to be investigated more. I should have said that this improvement, so if I go back to the hypothesis test for the standard model, this is stable against everything we can do. This is a next to leading order analysis of the data. So we've omitted higher twist corrections and then included them, makes no difference. We've increased the cut on the lower value of Q squared to 10 GeV squared, no significant difference. Standard model still strongly excluded. The chi-squareds I'm showing you differ from what's shown in the archive version because we haven't posted what I'm showing you here yet, because we made an estimate based on a suggestion from NNPDF of unknown higher order uncertainties by adding to the experimental errors the maximum variation in the theory prediction for each data point changing Q squared between 2Q squared and a half Q squared. The maximum variation over that range from the experimental value of Q squared is taken to be an additional error, which is added in quadrature to the experimental value. And so the chi-squareds we're quoting include that estimate of the effect of unknown higher order uncertainties. Okay, to summarize, way back in the beginning, I reminded you of something that's been known for more than 50 years, namely that the intermediate range NN force is a strong Lorentz scalar. A strong Lorentz scalar applied to confined quarks leads to a change in the structure of the nucleon. That's a profound change in the shell model. What occupies shell model orbitals aren't free nucleons. They're clusters of quarks with the quantum numbers of a nucleon, but the internal structure is modified. Modified little if the density is low, modified more as the density goes up. The scalar polarizability is a measure of that, a gross measure of that change, and it's the source of three-body forces, not just between nucleons, but between hyperons and nucleons. All of those predicted with no new parameter. We need empirical confirmation or rejection of this idea. And I talked only about the EMC effect and the possible spin EMC effect and other versions of the EMC effect that one could test, including an electron-ion collider. I didn't talk about the Coulomb sum rule, the longitude change in the longitudinal response of a nucleus, the change in the decay rate of a lambda in a nucleus, and so on. There are a number of tests that have been proposed. I showed you that a systematic study of nuclei using the most sophisticated energy density functional that we've been able to derive using this theory produces binding energies typically at 0.29% across the periodic table, super heavies at 0.03%, and describes the systematics of charge radii deformations. And I didn't show it, but the shell and subshell structure closures quite well. And finally, I talked about this hint from deep inelastic data of a possible new BSM particle. I need to acknowledge that the work on the QMC model has involved a lot of people, and I show some of the culprits here. Thank you.
Thank you, Tony. Again, on time, on the budget. Let's start with here. I'll come back.
Thanks, Tony. Very nice talk. Sorry, you were talking about this dark photon in the end, and I couldn't understand the starting point. Where does it get its mass? Is it from the same Higgs mechanism?
Yeah, it comes in the same way. Yeah.
Okay, but I don't know. Maybe my confusion is the same Higgs which is of the standard model.
Yeah.
But I remember that standard model Higgs, which is an SU2 complex doublet, and one of the degrees of freedom becomes the Higgs particle, and the other 3 degrees of freedom, which gives
but
the
we
mass.
haven't. We start with an additional particle, so we end up with an additional boson. The photon remains massless,
but
the Z gets modified, and in addition, you get this addition. You have this additional boson.
So there is not an
It
extra
doesn't
degree
change.
of freedom.
It can affect the Higgs mass, and that's a constraint you have to worry about.
No, what I was saying that the 3 degrees of freedom give masses to 2 Ws and 1 Z, and there is no degree of freedom left to give mass
No,
to
but we've
anything
put
else.
in a new
You put in
degree
by
of
hand.
freedom.
And that doesn't change the renormalization
Yeah, I mean,
properties.
nobody knows what's beyond the standard model, right?
So
this can't be the dark matter that fills the universe. But the way people talk about such a particle is that maybe something like this could be a portal, something that couples both to dark matter and standard model particles.
But it doesn't affect the renormalization property, adding the mass term, breaking the
Well,
gauge
you
invariance.
have to see the effect of this on a bunch of well-known observables, mainly around the Z mass, but also some B decay parameters. They're so-called 18 electroweak precision observables. I didn't talk about that, but I can assure you that this is consistent with those electroweak precision observables, at least in some regions of the epsilon space.
Actually, mine is not a question, is to give you an additional information because you talk about the polarized MFC effect at Jefferson Lab, and it is scheduled to run in FY26, so in less than 3 years from now.
It's good to see.
But we are, of course, building the detector because you have to have this polarized target.
It's good to hear. Thank you.
So, regarding the first part of your talk, nuclear, you don't like the standard model. One of the things the standard model has is a hierarchy problem. In a sense, so does nuclear physics, and you sort of go to the heart of it because it's really strange that the nuclear binding energy is 10 MeV, while the mass of the nucleon is 1 GeV, 100 times bigger. And as we know from the EMC effect, nuclear interactions do profoundly change the wave function of quarks. I mean, on the one hand, you have these two things about the mass and the change, and on the other, you have the fact that the binding energy is so low. what you said about the binding energy is that there is a cancellation between the scalar and the vector force. Is it sort of fine tuning to maintain the binding energy low, or is there a simple way you can explain this?
No, of course it's fine tuning. Yeah. But that's life. But I mean, you can't pretend that first year physics with with Lorentz transformations and Lorentz characteristics, well, it's first year graduate school probably. The difference between Lorentz and scalar and vector interactions, they're very different. And to ignore that is, in my view, crazy.
So I have one comment and one question. Comment is polarized lithium 7 or something like this in a collider. It's a great measurement. I understand the EMC effect with the polarized G1 function and the effect is large. But I think that needs a technical solution. And that is far from trivial, if at all realizable. Because you need to control the spin of this lithium-7 in a hard-on machine, and that is not something which is easy.
Mm-hmm.
So I think that needs really accelerator scientists to work on this. The other comment I have, if I go back to your dark photon and the impact you showed with and without to the PDFs, I find it very surprising that the impact is on the strangeness, the biggest.
Sorry, what do you mean?
The strangeness PDF. So before and after, if you look to your, there's very little on the the next here. The strangeness is huge. To me, a photon.
But if you look here, I'm not sure where this gray area goes. I suspect it covers most of that red area.
But still, it probably is that strangeness
They're
was
not inconsistent within errors.
Yeah, but that is a large effect. And I think it's probably because it's what is assumed is that strangeness has some connection to D and U, and you get some impact on this one.
Well, strangeness does have a connection to D over U because of the Cabillo angle.
Yeah, true. But that is
And
what
that's
probably...
been screwed up in earlier analyses. It's not here.
Yeah, no, but what I'm saying is it's probably artificial that you get this impact because of... Okay.
Sorry. Okay, thank you for the talk. I also have a question about this dark photon analysis. So if I understand properly, you add a term in your minimization, and that term has this effect of that you're showing here. But that term could just mimic something else. How are you sure that it is dark photon and not something else?
Of course it could. Nobody has, no one in our group and no one who's talked to me has said what it could be. I mean, we include or don't include the off-shell corrections, which are a very small part for the deuterium data. So we can put those in or take them out. We can include higher twist corrections or take them out. We can change the cutoff on Q squared from 1.69 to 10. And we've also added this uncertainty associated with the theoretical prediction if you vary Q squared, which is meant to take into account, what do they call it? Unknown higher order uncertainties, as NNPDF calls it.
But there's also a lot of different modifications that can come from methodology as well that could see a decrease in chi-square, right?
Yeah,
so here,
there's no way I can answer that question.
No, but what perhaps I'm missing here to see is there is a if and only if condition to show that it is a dark photon. So there is something that minimizes the chi-square, which seems to be obvious, and as Elko says, it affects the strangeness, but we don't really know if it's a dark photon or not. So what is the key point here to understand that it really is coming from the dark sector and not from methodology or other things?
Of course, if you ask me, could it be something that we haven't included that I don't know about?
Electroweak corrections. Yeah.
What?
Electroweak corrections. You could have corrections on the PDFs as well.
Okay. Which PDF analysis would you point me to that has those? See, what would be good is for other people that do PDF analyses to include this, see what they find.
Well, there is a lot of.
This has to be tested, right?
People have tried the SMEFT to fit PDFs together with SMEFT parameters.
Together with?
SMFT, this standard model effective field theory. And so it's different, but it goes in the same direction, trying to fit the parameters of this method, right? But people do that next to leading order with other corrections taken into account and different methodology as well, right? So,
well,
it's different for sure, but it goes in the same direction. So I don't know if it's what you mean by other people doing that. It was proposed already by two groups, by NNPDF and by CTEC, yes.
Yeah, look, that's why I'm not saying this is a discovery. What I'm saying is this is an interesting effect. It's a sizable effect. To the extent that we can test it, we found no obvious explanation. We've tried to take into account the effect of unknown higher order uncertainties by this variation in Q squared. I can't do more. All I can say is let others look at it and see what they find. And maybe we also need to look at other experiments which are more direct.
Tony, just shifting gears to the beginning of your talk, I am just wondering, nowadays, there is this ab initio calculations, I mean, non-relativistic for light nuclei, and you have, I was surprised that you look at to boron, a very light nuclei.
No, we can't
go. I'm just, is that more a theoretical curiosity? How we match this this image of the mean field, nucleon changing with quarks coupled to the mean field and so on. How do we match with this ab initio that is so spread out?
Well, the so-called ab initio theories, typically, if you fit the binding energies of light nuclei, there are a number of counter terms associated with the three-body force which are fit to that data. If I count on the slide that was shown earlier, there are maybe 10 or 12 data points fit, and typically four three-body counter terms. Now, I think Gauss said he could fit an elephant with 4 parameters. So, you can do it, and then you can use that theory to make predictions, and it works well as far as it's been tested. No objection. I showed you that the energy density function we get, it's a local energy density function. The only thing is the density dependence is more complicated, and that's derived from the underlying theory. But if you didn't want to believe in change of internal structure, you could say, well, this is the energy density functional I need for point-like nucleons. You could say that, and you could believe it. You'd be wrong, but you could believe it. Yeah, I mean, it's... If all you're trying to describe is binding energies, then there's no way to tell the difference. However, if you go to dense systems and you take the effective field theory built this way with a number of parameters fit to low density, because those light nuclei are relatively low density, and you extrapolate that to twice nuclear matter density and believe that you've got a reliable extrapolation, I have severe doubts.
From your description of the QMC, I get the impression that small changes in quark physics will have consequences to nuclear properties and more macroscopic observables. So what happens if you introduce, for example, QCD corrections in the quark interactions, or?
Well, what I showed you is for nuclear matter, the only way the changes enter is through the polarizability. Okay, scalar polarizability. In mean field, no Fock terms, that's the only place that the change in internal structure enters. So you could do a whole lot of things at the quark level, as long as you've got a similar scalar polarizability that's going to describe the nuclear structure that I showed you. So the nuclear structure is not sensitive. Not very sensitive. But the existence of the repulsive three-body force through that scalar polarizability is significant.
Any more questions or comments for Tony? If not, let's thank him one more time and break for lunch, and we'll be back at 2 o'clock. Is that right? Yeah, 2 o'clock.